And the second part is a work that was mainly developed by the group of Claudio Cañizares. We also are involved, but I remain or retain the mostly of the slides developed by the group. And this is closely related with the operation part. Yeah? And the main idea is, with the adapted version that I will show you, is to give you an introduction about the motivation to study stability issues, energy management system issues, and to give you some definitions, to talk to you about issues in the field of stability and control, and finally to give you an overview of some approaches for energy management systems. This is the aim of this second part. The introduction, a part of what I already mentioned in the first part, is this rapid development and increase of penetration of distributed resources are being integrated today in many forms of microgrids. It's not just the panel at home. Transition from a passive to grid containing only loads to this active grid, including all these DGs. And the hypothesis is that this will affect the dynamics of both transmission and distribution systems now and especially in the future. And this is the challenge related in this area. What we mean with DG stability, we mean that, or we understand that there is a lack of understanding of dynamics of DGs, particularly under unbalanced conditions. You will see that one of the distinguished or distinctive topics related with the transmission system is that we normally will face unbalanced system in the case of microgrids. This is not the case at transmission level. A full characterization of the unbalanced system in stability studies would allow a better understanding of the dynamic behavior of DGs. Most DGs nowadays are equipped with small synchronous generators, which must be considered in the analysis. And converter-based sources like solar, wind, and energy storage system are being deployed. This is the scenario. With this umbrella, the microgrid challenges are integrate high penetration of renewable sources, starting from mainly DGs, microgrids based on diesel generators or synchronous generators, so they move to high penetration of renewable. Low systems inertia. This is also the case in bigger system. You know, there is like a mythos. At the end, what you need is power to deliver. This is what you will have. You need to stabilize the system. But inertia is a clear signal of a challenge if you are not able to create a control system able to deal with the fluctuations. Rapid output fluctuations of converter-based renewable energy sources, which yield high frequency variations. And the need for expensive energy storage systems is today a challenge. Of course, we see for the future a cost reduction of the storage system, but if you can avoid this with other strategies, control strategies, of course, the results are very clear. It's a cost reduction and an improvement of the cost effectiveness of the solutions. In this introduction, our basic understanding of microgrids is the aim of this part 2. And again, definition, components, the idea of stability, controls, and energy management. And you can see a voltage and frequency control general scheme that you see here, the microgrid network as with the loads, the generators, and how you face, for example, in secondary control, other outputs that are used in this secondary to give signals, control signals to the network. And not only to the generators, you can also give signals, as I will mention later, to some loads. Okay, with this introduction, I hope you you are clear what is the scope of the presentation. Let us go to definitions. Here, the papers that are involved, in some of them I am also involved. This was the first output of this working group task force in IEEE, which deals with these trends in microgrid control. I don't know if you know this paper. In this paper, we explore or we summarize the input over around 3 years. I am the secretary of this, so I need to send the paper, the emails. Huh? You receive my emails if you are part of the network. And of course, if you want to be added to the list to receive, we are now working a new white paper for a new stability definition for microgrids. I am very happy to add you to the microgrid list. We have like a mailing system. So you can see what we have. We have this 3-level, more European concept from primary, secondary, and tertiary control. The different inputs that you have, and what we have as result is long-term set points for coordinated operation, dispatch commands to loads and units, and in primary control, output control on power sharing like troops. This is the general view as part of this paper in 2014. Definitions, we have the grid-connected microgrids, which is one world, and we have the islanding or the off-grid operation of microgrids, which is normally for us the worst case. And although you are analyzing a grid-connected microgrid in the islanding mode, you need to be very careful. So all what you learn from isolated microgrids are inputs that are valid for connected microgrids in our understanding when they operate in islanding mode. Okay. So grid-connected microgrids, voltage and particularly frequency control is not a major issue. This is the first message from us, as they are provided mainly by the grid services. So you will be supported by the grid. Second, DGs and PQ control mode is the current standard in this case, including non-dispatchable distributed generators like solar photovoltaic and some wind generators. So you normally go to like a PQ control, you have some power factor, you try to move with MPPT, with the maximum power, and you rely on the network to support this. The problem is when you need to be isolated, you need to have a very clear strategy for an islanding operation. And the third point is voltage control is being considered implemented by LDCs when DGs are low, examples photovoltaic. We go now to the islanding microgrid. Could be islanded or isolated, both. For both is the case. Voltage and frequency control are a major issue and must be implemented. And you will say that there is no clear separation between voltage and frequency. Voltage control is prevalent in most DG technologies, and frequency control is available and dependent only in diesel generator, microturbines, and storage systems. So normally what we have is the capability to achieve voltage issues, so control reactive power, but frequency is limited today. My opinion, this is a trend that is also changing. We are working a lot with some of our colleagues, Claudia, all this derating of PV to provide ancillary services like emulation of inertia, or more than that, to support the system with some control strategy, are today things that are more common to see. The past week was in Chile the first trial by Laborelec, by ENGIE, of the first 100 megawatt photovoltaic plant in Chile, providing they test the frequency control of the power plant with a derating to 30% of derating power compared with the MPPT, and the results are very interesting. They support the main grid. It's not a microgrid. So we are making with our ISO. This is perhaps a much more common strategy here in Spain, but in Chile, where we are not very fast to react to that, there are now trials to provide ancillary services. Of course, you lose energy, and you try to avoid that. And hopefully this is only very few % of the days or the hours in the year, but compared with the new investment, it's very clear if you can avoid a backup system, it will be a great solution. And this is what we are exploring, and this is also the case, in my opinion, in microgrids. But normally the frequency control is not available for all the DG technologies. Again, in voltage and frequency control, as more DGs of various technologies are added to microgrids, on or off grid, the need to coordinate control is important. In the field of primary control, you have isochronous mode or droop mode. In isochronous mode, control is shared proportionally to unit ratings, or only one is making the work. Works well for small number of units, but it is much more complicated if you increase the number of units and you start to face oscillations and so on. In the droop control, control is allocated based on droop constant, so that some react faster than others, but necessary with many units and is similar to the large microgrids, to the large grids, the same strategy that we use in the main systems. This is in the field of primary control. In the secondary control field, what we see is usually hierarchical centralized control similar to those found in large grids, like AGC, or the results of an energy management system in this case that apply to signals to all the units. Or you apply a distributed control based on agent-based control or distributed optimal power flow approaches. I hear from the first talk that you are working on agent-based control in the framework of this project. This is, of course, one very interesting approach. And finally, tertiary controls. The main objective is to optimize the control with an overall central or distributed optimization of the grid. Not widely implemented in large grids. They apply normally to voltage control only. It depends also if you define tertiary control as the economic operation of the system, then of course it applies with the power exchange or some day-ahead market. But normally, if you understand in the technical field, that then it is limited to voltage control, and it can be viewed as an optimal control coordination of multiple microgrids and their common grid. This is today a trend. You see many papers working how to manage a group of microgrids to deal with the system. This is today not a very a local challenge at the moment in Chile, because we are just starting with the microgrids, but at world level, of course. Those controls depend on the three ones, on the DG technology. Voltage controls are available in diesel gensets, microturbines, CHP turbines, voltage source converters like solar, wind, fuel cells, or double-fed induction generators based on wind generators, usually found in farms, or and also in battery storage systems. So you have this capability. And where they are not available in these induction machine-based solutions, and you say they are very old, but in microgrids, you find this as a solution. This was the case in our wind turbine in Guatacondo too. So this is today, because of cost, could be a challenge to incorporate that in small solutions, not in bigger ones. In the case of frequency control, the availability is dependent on diesel gensets that you have the potential to do that. Microturbines, CHP turbines, and battery storage systems can give you that. given their dispatchability and relatively fast response. This is the common situation. And normally it's not available in solar PV, wind, and small hydro, but as mentioned before, there are new trends with this derating strategy to have the possibility to support also frequency. I don't know at the moment if there are any questions. This is the umbrella with the introduction and definitions, and we move to the stability and control. Here, Claudio has a very long experience in, like our Watacondo, for our colleagues from Waterloo University. They work in this Casabonica lake. It's very well reported in several papers at IEEE. And this Casabonica is located in Ontario, as shown in the arrow here, and there's a picture on the left. And you can see the numbers of this microgrid. It's 10 times bigger than ours, so it's in the range of megawatts. You can see that we have diesel generators, not only one, so several ones. You have wind turbines, 4, and you have a PV array. This is the situation, and here the location of each one. Let me remember the store diesel generator. Yes, you can see the numbers and some distance. It's not too long, I hope. Unfortunately, I can't say, but I remember it's around 2 kilometers from one corner to other. It's to have a feeling of how big it is. And based on the question before, they have data loggers collected, so they have a nice history of information that can be used. You can see here the load in the system and also information from houses and different locations in the network that are available for analysis. There are different days. The spikes here, very interesting. It's very high consumptions for short periods, etc. And they also know very well the evolution of voltage. And the first message here, you can see that voltage is more or less in the range. We are looking the diesel generator plant in the voltage in the 3 phases, which are in the lower load situation and the percentile for different, but you can see here at the end the variations are low, but in current the variations are very high. So it's a clear definition of an unbalanced system. In the higher load situation for the same diesel generator, again in a lower level, but again you can see a high variation of current and a lower deviation of voltage, I would say, compared with the percentile 50. And for the 10 kilowatt solar array, which is near to the water treatment plant, you can see that voltage variation is, in this case, let me see, the current again show big changes, and the voltage also. This can be explained by the variations from the photovoltaic unit that needs to inject in the different hours, and it moves at the end the voltage to inject the power in the grid. Observations: current imbalance, as mentioned, significant, particularly in the summer. Seasonal changes do not allow to change transformer connections at generation plant to correct them. This is one of the, I can't go much more in the insights, because this is the experience from the group in Waterloo. I never visited the plant, but this was in several times discussed with with Claudio. The voltage profiles are flat, so you have no big variation of that. And frequency, small variations between 59.95, and it's impressive good compared with our results in Wataconda. It's good I didn't show you that, our frequency deviation. Renewable sources impact is small, given the relatively low capacity penetration at the moment is 7% of the peak load. So they never go fully renewable in this microgrid, but this is a very interesting reference case. Stability issues and modeling. Now I want to start to give you some insight, and please refer to these specific papers. You will receive this as PDF, so there are clear references. The first one I selected here in the material was to show how they model a three-phase power flow with a line impedance that are with the central one and variations with the factor K to show the unbalance, or to promote the unbalanced situation. And you will see this K factor in the rest of the presentation because they move that to show the impact of different analyses. Yeah? With this, the voltage profile and the loading margins and transient stability simulations in time domain, and to explore the critical clearing times, give a sense on how stable the system is. And this is exactly what we will show you in the next slides, exploring this famous loading margin. And normally with three-phase systems, all the phasor RMS approaches are not good enough, so you go in the more detailed analysis in time domain to look to the results. In the field of eigenvalues, many commercial programs use phasor models for small perturbation stability studies. Unbalanced generators show sustained small oscillations in steady state conditions, and thus standard phasor-based linearization techniques are not applicable. This is one of the claims. A simulation-based approach is necessary to study the problem using modal estimation with methods like the Prony methods or Steiglitz McBride iteration method. This is so the starting point of this analysis. You will see that later. And now, again, to like a remembering of the definition. Perhaps you know this very famous paper from the IEEE SIGRE technical brochure, where you have what we show in the lectures as stability analysis. And what we are discussing in this new, you know that there is a new group in the IEEE rethinking this. And there is a big discussion where Claudia from our group is participating in this discussion. They want to arrive, I think, in 2 years to a new definition of stability issues with the new world of renewals and converters, which is not in this, like, you know, inertia response. What it means if you have converters only, what is inertia? This type of discussions are today for the main grid. I am not directly involved, but our groups, yes. But this is we will say, the most valid definition that we observe. But if you look to the discussion that we have in this task force of microgrid, this is the current discussion. This is not the final decision of the new stability definition and what we want to share. But if you see, there is no more the paradigm, let me go back, of rotor angle stability, frequency stability, and voltage stability. This is not more the case. You don't have rotor angle stability in the microgrid, because normally the stability issues involve the frequency of the whole network. And this is why the colleagues arrive to this first approach to divide in two main issues: control system stability and power sharing and balance stability. This is today the discussion. There is a draft of the paper. If I add you to the list, I can send you the discussion, and we're asking for contributions. And of course, this is not the final work, but in both you will detect small perturbation, large perturbation. In the case of power sharing, voltage stability and frequency stability. And again, you can see distinction between electric machine stability and inverter stability. So you add explicitly this issue. And finally, short and long term. These are the new picture where the people involved in that, perhaps you are working in this issue and have a special opinion, and very happy to introduce that in the group. Stability unbalancing may lead to stability problems in synchronous generator-based microgrid, and now I will show you some results from these papers. In fact, from the first one, I will say here, excuse me. This paper from 2014 is stability analysis of unbalanced distribution system with synchronous machine-based distributed generators. This is not with high penetration of converters. And for this, they study, and this is like the super summary of the paper, the situation, and you have here the control scheme, like the unbalancing level that you can control with this factor K, the gain, phase compensation, and the voltage regulation. And the idea is introducing an unbalanced voltage stabilizer to the synchronous generator voltage regulator to improve the microgrid stability. This is the challenge of this paper. They convert the Japanese test system to this basic network with two impedances, the load and the SG and the connection to the network. When the system unbalancing increase, the loadability of the system decrease. And here, for you at the end, you can see, let me explain you. If you go to the different, you remember the K factor, which show you the unbalanced level? This is this. And you can calculate the maximum load factor or loading factor, and you can see the curve. And this curve is the balance situation, and the other three ones are how evolve the unbalanced condition. And of course, in the unbalanced condition, you will face one phase going to the instability condition. And this is the message that they show that for unbalanced system with an increased level of unbalance, you will see more and more decreasing level of loadability. This is a thing that can be interesting for operational studies. Here, more clearly, based on the critical clearing time, which again is a signature or a sign of stability. In this paper, they show that with an increase in K factor %, the CCT also decreased from 0.45 seconds to near 0.3. So you have reaction time until for the relays, but you can see that there is an issue with this unbalanced situation. In this same example, a high loading with some unbalancing with K 15%, the system experienced Hopf bifurcation in around with 1.91 hertz frequency, exactly in K15, which is here, where you see that the crossing of the real axis in the imaginary. So you can also study the poles of the system and show how it works. And they try to see what about the impact if I have a strategy like the unbalanced voltage stabilizer mentioned before at high loading and unbalancing condition of K25. So they are able to move this from 0.15 to 0.2, and the zero axis is here now. So the condition is better because of this strategy. The system is stable at high loading condition with this voltage stabilizer. Here with voltage stabilizer and without. And again, please refer to the paper. My mission here is to make the point, unbalanced, that you have some strategy, and there are some tools that are able to figure out that, and could be an interesting thing for your microgrids to do this type of analysis depending on the unbalanced level. This is also related in the second paper to DFIC. So they study this type of effects with the rotor side converter and the grid side converter, and with the same strategy for voltage stabilizing. In this case, you have this PLL strategy involved in the new control scheme with this wind turbine, this DFIC. And when the system unbalancing increased, the maximum loadability of the system again decreased. So the results, without going now in the details, remains in the same tendency, and you can improve that with the stabilizing of the system. Here you can see the classical control scheme is S1 for the first time period here. Then limiting the electrical torque oscillations, the second, and limiting the stator active power oscillations. So, and if you add in S4, S5, and S6 is in the next picture, I think, and you can see the different behaviors, and it's a clear connection between the limits that you impose and the strategy. Here you can see that. S4, S5, how it evolves with the different strategies, making a much more better behavior of the system with this voltage stabilizing strategy. Again, in the case, the CCT at base load for a three-phase to ground fault decrease with the increase of unbalancing. So again, unbalancing key message for microgrids. Normally not too easy to cover in a first view. Moving to other issues related with reserves. Genset reserves are required, especially with variable sources. In the experience from the group of Waterloo, they define, and you know, this is also numbers that we apply to main power system, is 10% load without renewals, 25 of PV power output, like the reserve, or 50% of wind power output are numbers that are on the table related with reserve requirements. With high penetration of renewable energy storage system is required to help regulate these variations. Isochronous and droop controls are commonly used to share load among generation plants, and droop control has been proposed for energy storage system. This frequency control test system was developed for this SIGRE benchmark. I think you know this network with a total load of 7 MVA, 2 synchronous machines, 3 distributed energy resources. Synchronous machines are master control. Voltage frequency control is located on synchronous machine, and it was modeled with PSCAD. What you can see here in the picture is how the aggregate wind power moves in this time frame in seconds. And you can see that the results without or with the base control is more or less that the frequency follows the variations of wind. Let me go back here. You can see very similar. With the storage control, you see that. And with the voltage frequency control strategy, you see the other line. How it works? Studies have been carried out by EDF at the Archipiélago de Guadalupe of impact of genset on voltage frequency. There is a paper with this reference here. I don't know if the people from Guadalupe were involved in that, but I can identify any of the authors. Perhaps you know some of them here. This is the microgrid in this case where they studied this voltage frequency control. There is diesel generator here, which is the Jari North, important because of the next slide. The microgrid evolution with the diesel generator, excuse for the small picture, diesel generator in dark, combustion turbines, and diesel in red one is the bagasse coal, and embedded PV is wind plus PV is the green one. So in this case, to show you how it works, you have a disconnection of diesel unit at that point, and in this point they activate the activation of automatic voltage regulation with the set point that is changed based on the strategy, and it means that the voltage of the generator JN4 is the generator that I mentioned before, the diesel generator. So there is a strategy to decrease the voltage, and the impact of that is that the frequency recovers. That's the study behind this. There is another study, in this case led by the group in Waterloo, frequency control in isolated island microgrid through voltage regulation. And the nice message here is, if you have a voltage dependency of the load, for example, NP 1.5, then for a normal situation and with a control of 5% of the voltage in the voltage strategy, you can achieve a variation of 7.6% of the load. And this was the motivation to explore how effective can be this strategy, moving the voltage to cover stability issues in a microgrid. And this is the control scheme. And with the same picture as before, you can see that the results here with the generators, with the voltage frequency control of the genset, can reduce in this line compared with the other one, only with the management of the load voltage dependency. So you can move here in a nice way with this capability, and you can exploit this. Again, try to avoid storage or to increase the cost in the system, and only if all the strategies are not enough, then you go in new investment. This is the idea. Effect of voltage regulator, voltage limits. Again, you can see if you have in the voltage regulator, you fix the limits on this, or you move a little bit the range, you can achieve a very good recovery of the values. This is the voltage and the frequency. This is the previous one with all this excursion of frequency. And with this management from the equipment, you can have very nice results in this common strategy. Effect of load composition. If you have 1.2 or 1.5, to show you, of course, with this, you have more space to play. And with this, a little bit more, so you can see more variations. But at the end, very interesting to know how the type of load that you have in the system in this specific microgrid. Voltage profiles are fairly flat with proper voltage regulation. Hence, voltage and feeders are not a major issue in microgrids. This is a first conclusion on this topic. Load unbalance, loadability of the system decrease as unbalancing increase. Eventually, critical poles cross the imaginary axis and the system becomes unstable. Second, the system is less transiently stable as unbalancing increase. Classical phasor models and tools are not appropriate to analyze and understand stability in microgrids. And proposed voltage strategy is simple and improves microgrid stability. These are the key messages of this section related with stability. Related with, again, if I go back, we are talking about voltage, load, about frequency stability, not an issue with enough generation set reserves. With high penetration of variable renewals, energy storage system is required. This is the conclusion of the experience of the group. And the voltage frequency control, it has been demonstrated in a real large microgrid that load power voltage dependency can be used as reserves to control frequency. Proposed voltage frequency control acts as an additional control to conventional frequency controls, decreasing dependency on energy storage system as potentially yielding in savings on the system. This is only to summary what I already mentioned before during the presentation of the graphics. More or less. The final part is, okay, you know, stability is a world, so it's only to give you the flavors from the insights recognized by the group of Claudio Cañizares, and could be interesting to promote some discussion. And in energy system, energy management system, I think to finish at the right time in this 8 minutes, I will go a little bit faster, because what I will show you is the umbrella or the different approaches for energy management system observed, not at commercial point of view, it's more in the different avenues of research, with uncertainties, without centralized, decentralized. So please let me go fast, and perhaps we have some minutes to discuss and come back to some slides. What is an energy management system? It's a set of protocols and computer applications designed to assist power system operators in the operation of the grid, including state estimation, optimal power flow, voltage control, reactive power optimization, security assessment, load forecasting. This is the whole package. Oops. The challenge: in microgrids, all the EMS applications must be performed by an autonomous, automated system. One of your questions. This is the target. If not, it is expensive, especially in a microgrid where you can't pay 24 hours supervision from an engineer team. So you need to be hopefully autonomous. The operation of an energy management system in a microgrid becomes more challenging due to the critical demand-supply balance, low inertia of the system, non-dispatchable renewable sources, and the presence of energy storage systems. So this is a special challenge, not the same as in the big power system or the huge one. The general energy management system case, find the optimal or near optimal unit commitment for the units, find the optimal or near optimal dispatch of the units, find the optimal or near optimal voltage settings. These are the outputs that you expect from an EMS. And the challenges, again, intermittency, system states are coupled in time because of the storage. So not only where you start the unit, which is the unit commitment, is also related with the coupling with the storage, that you have a state of charge and also state of health, in fact, that you need to take care. Multiple objectives, you can have more than one, as mentioned in the design part, in part one, total cost emissions, multiple owners, and sometimes conflicting objectives. So it's not easy to deal with all the structures that we observe. We have here a decentralized approach. If I understood, this is the approach that you are following. In this case, a very market-oriented, that consumers, energy storage, and distributed generation, the coordination is the price. Buying, selling, and they define something, and what you make in the different market spaces, you can announcement of main grid prices, you react, and bidding plus market settlement, and in the next period, the same one. This is the decentralized way. It can work very well if you are connected to the system. It will not work if they are not connected, because you rely on the support of the main grid to that, and it works. In the same paper, the strengths of microgrid control, we also show that what the decentralized approach in the normal or general centralized approach, where you have a centralized EMS and you have the outputs I mentioned before. I will not repeat this, but you have advantages and disadvantages of this approach. The advantages of a centralized approach is allows the implementation of traditional optimization methods, able to handle multi-period optimization because you are managing the whole information needed, more suitable for standalone operation when demand-supply balance within the microgrid is critical. Disadvantages obligates the different actors to share information about operation, costs, and constraints. Difficult to implement in a multiple owner microgrid with different and conflicting objectives, and the energy management system needs to be readjusted when more units are added. Today, you will see many, many papers discussing this. And we are working also with some PhD students trying to, this heterogeneous network, how to be flexible in the centralized approach. We already use only centralized approach in our networks. And all the next slides are a trouble looking for the different approaches. I will show you only the titles, and to arrive to the advantages and disadvantages, and at least you have the list. First, the general deterministic EMS is the basic one with all the structure. You have a model predictive control, what we call MPC approach. Again, could be deterministic, but they use a window, sliding window like this. You can see that very clear here. And the idea is that you will only use the first result of the optimization, but you are taking into account a period, and you readjust. And in that way, you take care in some way about the uncertainties, because you will not have a final definition for the whole day. At the beginning of the day, you move with the window and you look to the uncertainties that are showing the real results. There are here some examples. Unfortunately, I will skip this only to show you here EMS in an unbalanced network, again, a balanced network. So they show a specific application, and the results seems to be similar, but you can see here that the black one, there are some changes in the treatment if you work unbalanced or balanced. There are a second model in the EMS deterministic model 2, which is composed with a nice addition. So you have the MEMS, which is unit commitment plus optimal power flow, but you have a smart load estimation based on neural networks that is able to have a load profile, and you can have some reaction of the loads. So you have some flexibility on the loads, and again, it will impact the results and the flexibility. I will skip this, excuse me. Here only dispatch with Pmax without Pmax. Pmax is this module able to readjust the load with the flexibility, and you can see a real impact on the system operation. You will face in the literature a wide field how EMS take into account uncertainties. One, again, the sliding window is one of the approaches. Wait and see is the idea, deterministic, but with this window, like the MPC I showed you previously. There are stochastic optimization approaches explicitly that are incorporated in the network. An advantage in the microgrids is if the microgrid is not too huge, all these things that are unfeasible for big networks are feasible for small networks. You have the computer capability to go much more in detail because you have the information, you have real time, you know the people in EPFL, they work with PMUs, a special type of PMUs adapted for, you are in the same location, so you have not the problem of or too many problems of delays. So there are advantages if you are in the same territory working on a network. You can make use much more of this strategy. In the paper or in the report, you will say the affine arithmetic-based optimization, which is like fuzzy arithmetic, is type of mathematics used where you define intervals where the variables can move, and with these bounds you can have some optimization. You have this model predictive control and receiving horizon control as a strategy. This is a more clear view what I mean with the different windows for optimization. You have stochastic unit commitment with this type of approaches, and excuse that I will go very fast on that. Only the general structure of the optimization problem you need to solve. And related with this topic, you will see here the results, but let me go to robust unit commitment. Is again a very interesting where you have like min-max structures. This is also used for protection system. Robust optimization, you want to ensure that you have two objectives, that minimizing cost, but hopefully to reduce the maximum time of cleaning time from the protection. And so you can make both in one optimization. Normally, you transform that in a conventional optimization, minimization, but you add a variable like this, which is with a new constraint, you can ensure that you have a min-max like a robust optimization. And could be interesting to promote solutions against some important uncertainties. This is the robust. I skip, we are in the time. Affine arithmetic, as mentioned before, is a specific mathematics developed for to deal with an optimization of costs of an EMS. And let me arrive to the summary of that. Various, an excuse for the very quick overview of all these tools, various EMS models for isolated microgrids have been developed based on decoupling the problem is sequential, mixed integer linear programming, unit commitment, non-linear OPF, etc., with different horizons and update rates. For the unit commitment, there are some advantages of MPC. It's the easiest to implement. Adequate performance results on lowest reserves by highest possible load shifting, shedding due forecast errors. This is as expected. It's a deterministic approach. This is the most normal use in the first solutions of microgrids. If you go stochastic programming, more complex to implement but manageable. Adequate performance, if not too many scenarios, requires these probability density functions, assumptions, and proper selection of scenarios, results in more reserves and little load shifting shedding. So it seems to be more robust in this sense. And you will see here robust optimization and affine arithmetic with similar conclusions. So at least you have a first reference where to move with the different approaches. The same for the optimal power flow. Part of the EMS evaluated for affine arithmetic and also for this robust optimization. And with this, I arrive to the end of this second part, which the idea was to go more deeper in technical issues. And I see in the program that you will go after the lunch much more in the experience of technical issues. So it's complementary. Jose Luis, thank you.